Good morning. So I'm going to walk through some problem-solving strategies for the AP Physics 1 exam. So when you're looking at a problem, what are we thinking about? What units are we thinking about? And what is important to remember about those units? As well as give you some tips that I just learned about the new 2020 exam. So in the immortal words of Douglas Adams from the Hitchhiker's Guide to the Galaxy series, just remember, don't panic. They're going to give you probably more questions than you can do in the allotted time. Just because you haven't done all the questions doesn't mean you can't earn a 5. The purpose the College Board has stated for giving you a lot of parts to these questions is to give you an opportunity to show what you know and to earn points. So don't panic if you don't finish a problem. Don't panic if your computer is like not moving as quick as you want, or you feel the timer isn't starting as quick as you want. As soon as you see that first question, a 30-minute timer will start, and you will need to stop your work at 25 minutes and start to submit. So that timer will turn red, and you will need to use those 5 minutes to submit your responses. If you do not submit in that time, you will earn 0 credit. So you want to take that time to submit what you have to earn the credit that you can with the responses that you've created in the 25 minutes. Do not use 4 of those 5 minutes to try to keep working, okay? So stop at 25 minutes and start to submit. For the next question, you have 20 minutes to do the problem and submit. So actually you have 15 minutes to complete the problem and 5 minutes to submit. So this exam is actually 40 minutes of work in length. I also learned that you can do all of this year's exam with just the ability to type, but you don't have to, but you can. So because you can answer every question with just the ability to type, that means there'll be no graphing, no drawing diagrams, and no lengthy algebraic manipulation or derivation. So that is kind of good to know. And the practice test number 2, which consists of 4 questions amounting to essentially 2 practice 2020 exams, asks you to type your responses to those questions to get an understanding of what questions might look like that just require you to type and how you might respond in that way. So what we're going to do is we're going to look at some questions and talk about the units that they might apply to and big ideas from those units. So here's a question where we have, just from the picture, we can see there's 2 cars, one is moving, one is stopped, and we can see that we might need to make a velocity versus time graph. So now while this isn't going to be something that is on the 2020 exam, you might be asked to interpret another student's velocity versus time graph that they've made and critique it. So what might we want to think about? This is clearly a 1D kinematics problem. It has objects moving, accelerating under their own forces from engine. Other examples might be like a person running. Key strategies are list what you know and choose one of those big 3 kinematics equations on your reference tables to help you determine what the question is asking about. Since it's doing a motion graph, I want to review some key concepts about motion graphs. Velocity can be found from the slope of the displacement versus time graph or a position versus time graph. And if 2 objects, so if we had to plot both the truck and the car in that previous question, if they have the same slope in a displacement versus time graph, that means they have the same speed. However, if they have the same slope in a velocity versus time graph, that means they have the same acceleration. And then one more thing we can learn from graphs or demonstrate our understanding with a graph is that the area between a velocity versus time graph and the x-axis gives us the displacement. And that is kind of the area between the x-axis and that line. So I have a diagram here summarizing these, and I'll make this PowerPoint available as well as kind of a shorter Word doc available. Flattening curve in a position versus time implies velocity becoming less negative or closer to zero. A negative slope implies negative acceleration, and this area is displacement. So these two graphs show the same motion in position versus time and velocity versus time. Let's look at another question. We have two spheres leaving the table at the same time from the same height, and we want to know something about them. It's a classic physics question. We did this as an experiment in class. So this one is dropped. This one has a horizontal velocity. And what do we know about these sorts of problems? So it's not always like two spheres shot and dropped. It could be like a car taking off from a ramp and then another car taking off from a ramp, but the table is the same height. We know the vertical displacement is the same. We know that they have the same vertical acceleration and the same zero horizontal acceleration because there's no force acting on it while it's in the air. There was a force to get that first ball moving, but as soon as that is moving and that is no longer touching the ball to accelerate it, that force is no longer acting, and gravity is the only force acting, and it's only acting in the y direction to cause it to fall down. So with the same vertical displacement, the same vertical acceleration, and the same vertical speed, they should hit the ground at the same time. But with that time, the one with the greater horizontal speed is going to go farther because it has a greater initial horizontal velocity than the other one. It is important that you state these three things, same vertical displacement, vertical acceleration, vertical velocity, initial vertical velocity, and imply that this equation means the time is the same if you're given a problem like this. Let's look at another one. So in this problem, we have a plunger. I think this was from one that I already assigned, like the 2019 FRQs. And the plunger accelerates the block and is touching the block from block 1 from point A to point B. And so the only force that acts on this block from point A to point B is the applied force. And then from C to D, the only force that acts on the block is friction. So this is a problem that clearly is interested in forces, maybe a little kinematics, because forces, as we know, through the best equation ever, the net force equals ma equation, forces are related to acceleration. So if we're sliding on a flat surface with only like one force acting or friction acting, for example, skier encounters a rough patch in the snow, or one like we just saw, you can use a kinematics and forces approach. So if we just have friction, then the force of friction is the only force acting, and it opposes the direction of motion, and we can set it equal to mass times acceleration. That means there's a constant negative acceleration, and because it's a constant acceleration, it has a linearly decreasing speed. A problem like this might also ask you about some work done or the distance that skier goes or something like that. And you can use an energy approach where the force of friction does the work for that distance and it changes the kinetic energy of that skier from whatever it was, 1/2 mv squared, to 0 if it's stopping. And it takes that kinetic energy and turns it into heat. So this would be a work equals change in energy approach, and the force of friction times the displacement that the force of friction acted to stop it equals that negative kinetic energy, because it's V or E final, which is 0, minus E initial, which is 1/2 mv squared. So this is a constant force, again, constant negative acceleration, linearly decreasing speed. If we doubled the speed here, it would take 4 times the distance to stop that object. And you can show that through kinematics, or you could show that through work equals change in energy approach. keep it moving here. We've got an inclined plane, interesting, and we've got a wheel with spokes rolling down a ramp. And here's another one. Got another inclined plane. This is from our practice test. And the student hits the block. It goes up the ramp, and then it goes down the ramp here. So what are we thinking for these? Well, we've got a ramp, and there's a couple. This one talks about the static force of friction. This one we can see it's asking for a free body diagram. So it's likely we're going to have to look at forces. So if we have an angle theta measured from the ground, we know the following things. And these are things that, you can have this on a cheat sheet printed out for you during the exam, but you don't want to use the same words that I use because you could be flagged for plagiarism, but this is all good stuff that you know. The component of the force of gravity that points down the ramp is mg sine theta. If it's at rest or if it's sliding down the ramp, friction opposes that motion and points up the ramp. At rest or at constant velocity, the friction pointing up is equal to the part of gravity pointing down the ramp. The normal force is always perpendicular to the ramp and equals mg cos theta. And with no friction, we actually know that the acceleration is equal to g sine theta. However, with friction, the acceleration is less than g sine theta because there is this force opposing it. So it goes slower than if there is no friction. And we can think about that from a little bit of a kinematics perspective, that less acceleration means a lower speed from our v squared equals v0 squared plus 2ab equation. Now, with the inclined plane and the object that was rotating, it's likely that we also might want to think about this as an energy problem. So this mass is like going on a little adventure. It's going down the ramp, and that's something that should trigger our brain to think about energy. So it had some initial potential energy at the top, and it will have rotational kinetic and translational kinetic at the bottom. So for a block, E equals EF, no friction, gravitational potential equals kinetic, but with friction, we want to think more about the work done by friction being the energy loss. And that's similar to what we had just talked about with sliding on a flat surface and friction. For a rolling object, friction converts some of the energy that was stored as potential into rotational kinetic energy. So now the final energy is kinetic rotational plus translational kinetic, and it ends up slower than if there was friction because some of that stored potential has to end up as kinetic. If there is no friction, however, there's no torque, there's no rotation, unless it's like already rotating to start, and it moves just like a frictionless block. Now, if it's going up the ramp, we've got some other interesting things, which it actually is doing in that practice problem from the practice test number 2. So as that block moves up the ramp, not only does gravity oppose its motion, but friction also opposes its motion as it moves up the ramp. So you've got kind of a greater force down the ramp opposing its motion as it goes up the ramp than we might as it goes down the ramp, because friction opposes its motion down the ramp, but gravity actually helps accelerate it down the ramp, if that makes sense. For a rolling object, this is really interesting. So for a rolling object, I've got a rolling object here. If it's going up the ramp, right here, the object itself is actually moving in this direction up the ramp. You can think about it that way. And so the friction opposes the direction of motion, which is clockwise here. And so the friction points up the ramp. And so the friction actually acts to slow down the roll and creates a torque on a rolling object going up the ramp, and that's what helps it convert its rotational kinetic energy back into gravitational potential energy as it goes up the ramp, if there is friction. Here's another problem. So we've got some interesting things here. We've got a spring and a mass attached to that spring on a frictionless surface, and the block is oscillating with a period and a given amplitude about the spring's equilibrium position, and then they drop another block on top of it. Very cool. So it asks you to determine the ratio of the period of the spring's oscillation with both blocks versus just one block. So what are we thinking about in this problem? So we've got a spring and we've got oscillations. So if we have a pendulum or a spring oscillating, probably we want to think about energy at some point. If it's a pendulum, that gain in gravitational potential energy that it has as it falls down and loses that gravitational potential, the ball gets more kinetic energy. With a spring, if we stretch our spring out, that gain in spring potential energy eventually gets converted to kinetic at the equilibrium position. But in this case, that first question asks about the period. So we just want to refer to our period of the pendulum or period of the spring equations. So we can express the period of the spring equation for the block with just the one mass attached to it. And we can express the period of the spring equation with the block, the additional block on it. So that's 3m total for the mass of on the end of that spring. Then we just divide those two, do a little bit of algebra, and that's about it. So the period only depends on the mass and the spring constant. It doesn't depend on the amplitude. However, if it's going to ask us about the amplitude, or if it's interested in the amplitude, that's where we want to use energy. Because in the spring potential energy formula, we have a way of thinking about the amplitude, which is the change in the spring length, the amplitude. Let's look at more questions. We might have a collision question. So with any collision question where one object hits another object, we want to think about momentum. It's a good place to start. Anytime there's collision, if there are no outside forces, momentum is conserved, which is very useful. If there are outside forces, then we could use like an impulse equals change in momentum equation or analysis to that. It's also probably useful to think about energy in any collision. Unless it's an elastic collision, kinetic energy is not conserved, and so you can't use conservation of energy with collision. So you want to start with conservation of momentum. And if we have a moving object striking a stationary one, the one that like bounces backward has a big change in momentum, the biggest change in momentum, because it's going from a positive velocity to a negative velocity, and that's a very large change. So a difference from +2 to -2 is a difference of 4, which is a large change in momentum. The stationary one will also end up going really fast because that change in momentum, let's say from if it's a 1 kilogram object, that -2 to 2 scenario was 4 kilograms times meters per second. So that one that was initially not moving, if it has the same mass, 1 kilogram, it's going to end up going 4 meters per second. So it will end up going the fastest since the change in momentum must be equal because they have the same force applied for the same period of time. A little bit of impulse equals momentum. Another from our practice test, the last question, we have a satellite going around the Earth and it's moving clockwise. We want an equation for the period, we want to draw forces on it, and we want to compare the period if we change something about it. So this is an object moving in a circle, This is an object that involves universal gravitation and circular motion. So for any object moving in a circle, the net force is always towards the center. So that's the first question, draw the net force on the spacecraft. When writing the force equation, make positive always towards the center. And then that net force for objects moving in a circle is mv squared over r. If it's moving at a constant speed, you can always think about v equals d over t. And for our circular things moving in a circle, that's 2 pi r over the period, where r is the orbital radius. If it's a vertical circle, so this is just a different scenario of an object moving on a circle, like keys swinging on a lanyard, if there's no external force, energy might be an interesting way to look at that. So it's similar to a pendulum, but it's going all the way around. So the kinetic plus the potential at the top equals kinetic only at the bottom if you define the bottom of that circle to be your zero or ground point. If it's like a Ferris wheel or something with a motor, then there is an external force, so you can't use conservation of energy. So that's a different case. Last one, we've got two pulleys here. One is a solid disk and one is object with mass located on its outer rim. And we've got spring scales measuring force, and both can rotate with negligible friction. It says they're both at rest. They have the same constant force causing them to rotate. Which one will complete the revolution first? So we've got objects rotating about a fixed axis with a force acting on the outside of the axis perpendicular to the radial line. So this is clearly a rotation question or a spinning object question. So a couple things to remember about rotating or spinning objects. If there's no outside torque, angular momentum is conserved. That's not the case here, but if there is no outside torque, like with our divers or with our figure skaters, angular momentum is conserved. So if the moment of inertia changes mid problem, like a skater pulling their arms in or the diver tucking, the angular speed can go up. And you must justify that by saying that the angular momentum must stay the same, but the moment of inertia changes and the angular momentum must stay the same because there's no outside torque. In that same example of the skater pulling their arms in, the rotational kinetic energy will increase. So the work done pulling the arms in causes the amount of energy in the system to go up, coming from their muscles and the food they ate. And the rotational kinetic energy is 1/2 pi omega squared. The increase in omega matters a little bit more because it's squared than the decrease due to the change in moment of inertia. If we're comparing two objects, the one with the mass distributed on the outside has a greater moment of inertia. So that's just like the problem we saw. It will take more work to spin this object. So it will take more work to spin that kind of wheel with the mass all the way on the outside than it does to spin the uniform mass disk. So there'll be less energy left for other forms. So there's more energy in rotation, so it won't be able to move as quickly and end up going slowly. If something starts spinning faster or slower, then there must be a net torque to change its angular velocity. So if it got faster, like you applied oil to the axle and it was able to move faster, then there must be a torque applied as there is an increase in angular acceleration and a linearly changing angular speed. Alternatively, you can think about the playground equipment, like if you're just applying a net torque on the outside of that spinning disc with a bunch of kids on it, you are causing it to go faster. If maybe there's some friction slowing it down at the axle, then there is a torque applied as well. So that was a fast run through of a bunch of problems and a bunch of things to remember for each type of problem. I'm going to summarize this in a Word document that's like 1 page front and back, as well as give you access to this PowerPoint that I made that has all of the questions that I talked about. And I am here for you if you have any questions. I hope this was helpful. Good luck. Have fun. I'll see you soon.